In this set of video tutorials, we're going to learn how to work with serial communications. With the Arduino, we'll actually send some information from the Arduino to a serial monitor program to our PC so we can see what's going on inside the Arduino. And then we'll send some information from the keyboard, our PC's keyboard, to the Arduino. That'll be parts 1 and 2. In part 3, we're going to transmit some data from Arduino to processing, and then in part 4, we'll see how to do it the other way, from processing to transmit some data to Arduino. Giving you a link here, SparkFun has a nice little serial communication tutorial if you want to take a look at that. Right. And when you connect your Arduino board, right, we've been connecting with a USB cable. Right, we've been actually then this USB cable connects to our computer where we have our Arduino software installed, that IDE, and we download. We use the in our previous lab when we created the blink LED sketch, we downloaded our program through the USB cable to the Arduino. Well, USB stands for Universal Serial Bus, and we're going to use that to transmit information back and forth so we can physically debug what's going on in our hardware. Notice with the Arduino, we don't have any sort of output screen. Right? If we don't attach special hardware, we don't know what's going on when our program's running in here. So serial communication can be used for debugging. Right? It's used to transmit information to other programs that might act upon that information as well. So we'll see examples of that in our future labs. So on the Arduino board itself, if I come back here, this actually has a special chip that can, this has a special chip right here. So I don't have that circle right in here. This chip actually controls, this FTDI chip, controls the information that's being transmitted from the PC and the Arduino IDE through the USB cable. Right. So that's this connection here. And what's being transmitted are a series of binary ones and zeros. And they're transmitted one at a time, one following the other, then as serial communication. Right. So there's a physical transfer of data. We call that a digital bit stream, right, over a point-to-point communication channel. And there's different ways to do it. There's serial and there's parallel. When we say serial, we send a byte of information, and that's sent one bit at a time. In parallel communication, you still send a byte, but you transmit all the bits in parallel. So here's an example of serial communication where the bits are being transmitted one at a time, one right after the other. In parallel, and notice that there's one line here for this connection. This one on the left is transmitting to the one on the right. Over here, this one on the left is transmitting to the one on the right. But in this case, there are, 8 communication lines, meaning 8 different bits are being transmitted at the same time in parallel. So serial communication then takes less transmission lines. It's also easier, takes less synchronization as well. Parallel communication takes a little bit more hardware. And our focus then in this lab will be on serial communication. We're going to work with what's called asynchronous data transfer, meaning that both devices don't have to be completely synchronized between their clocks. Right. An example of asynchronous communication is if you and I were holding a conversation. There might be times if both of us were sitting there silent, we weren't saying anything, we would just be doing whatever we're sitting there doing. Right? But if one of us begins to speak, then the other begins to listen. So one of us, the speaking person is transmitting, the person who's listening is receiving the information. Right? So that's what this data is saying. If one process, right, begins to transmit, then process B here begins to listen. A can continue working, right, and after it's transmitted, it can continue working and wait until it gets a response from B. So notice it can continue doing other work in terms of asynchronous. But in terms of synchronous communication, when A transmits something, it sits there and waits for a response before it does anything. And we want our hardware to be able to do other work, so we use asynchronous communication. So the receiver, right, and the transmitter, well, the receiver must have a way to distinguish the difference between valid data and noise, right? So if you think of the physical line connecting the two, right, we think in terms of digital zeros and ones. there's a voltage on the line. So depending on your communication protocol, it depends on what the voltage is. Well, there are electrical signals on that line. And if you think in terms of data between zeros and ones, the receiver has to know when the transmitter has started transmitting some information, right? So what the sender and receiver do is they agree on timing parameters in advance. So think of the transmitter is going to tell the receiver how fast they want to transmit the data, right? Whether there's any special bits, how many data bits there are, and the receiver side has to be set up in the same manner, right? They both agree on this communications protocol and they follow it, and they're able to transmit the data. Right? So normally what happens is then there's a start bit that marks the start of communication. Right? So clocks at the transmitter and receiver are both responsible for dividing the data stream into bits, right? These clocks are not necessarily synchronized, right? Device A, device B, they have their own clocks running, but they've agreed on a clock for the rate of transmission, right? And there's this physical line connecting the two. And whenever there's a change in that line that represents the start bit, then, so the transmitter, when it starts transmission, in this case, if you look at this, the start bit, if you think of this line here is high and this line is low, then the transmitter takes the line low. So there's this line in between the transmitter and the receiver. If they both agree that the line is held high when there's no transmission, when the line goes low on the transmitter side, well, the receiver is going to detect that. And when it comes to referring to voltages, there's mark and there's space. Mark represents a digital 1, space represents a digital 0. All right, we'll just worry more about the 1s and 0s. And so the fact is that this receiver is responsible for reading the data bits. The transmitter then is responsible for transmitting them. And since their clocks aren't perfectly synchronized with each other, right, they have to decide then on what the period is. So the bit period then is the shortest time for which the line may be in a logical 1 or a logical 0 state. When the transmitter is going to transmit a word, so as I said here, when it wants to start transmitting, it places the line in the 0 state. So this goes from the mark or the 1 to the 0 state for 1 bit period, right? Whatever that period of time may be. And when the receiver receives this logical 0, right, called a start bit, it knows that a character or some sort of data, I said a character, data is about to follow. Right? And then the rest of the data stream here is divided up into these different bit periods. So let's take a look. This example has 7 data bits. It has 1 parity bit and 1 stop bit. So 1 start, 7 data bits, 1 parity bit, 1 stop bit. So when you first set up the serial communications software, hardware, you both agree on how many characters will be transmitted for every single byte. And in this case, 1 start bit, 7 data bits, there's 8, parity bit 9, stop bit 10. There'll be 10 characters, or it will take 10 bit periods to transmit then an entire character. As I said, the clocks are not perfectly synchronized. What the receiver's doing is it's just going to sample. It knows what that bit period is. It's going to sample regularly during that bit period, once during that bit period, and read the signal to see whether it's a 1 or a 0. What we use to transmit data is we transmit the data in an ASCII format. So we've studied some ASCII in our study of C. Right? Communication uses 3 transmission lines: signal, ground, transmit, and receive. Right? So 1 line to transmit, 1 line to receive. So a person then can both have 1 line they're transmitting on, a piece of hardware. 1 line's transmitting on, another line that's receiving on, the 3rd line will be grounded. And that's handy because when you have 1 line for transmission and 1 line for reception, you can transmit, right, while receiving on another. Right. So the ASCII code, if you've never seen it before, it's a standard for deciding how to transmit, how to represent numbers, digits such as 0, 1, 2, 3, letters of the alphabet. Right, so the printable characters as well, you have to have a way to represent that in computer memory. So here's an example of an ASCII table. we can see that if you were to, the space character is a decimal 32 or a hexadecimal 20. Right. You can see then that the 0 character is stored in memory as a decimal 48. Right. 0 through 9, each one of these are contiguous, so 49, decimal 49 represents the character 1. Right. We can see greater than, less than, so lots of all the typable characters are printable characters. Here's a capital A. Capital A will show up as a hex 65. A capital Z is a hex 90. Here's some control characters on the left that were related to printers, right? Things like that we won't worry about. Here's the lowercase alphabet. A baud rate. This is a term that you're going to know from setting up the serial port. You're going to have to agree on a communication speed. So it's the speed, right, at which the link operates, and it's expressed in bits per second, or BPS. And the range goes from 110 to 56,600, but there are other speeds as well. Right. And for our purposes, bits per second and baud will be the same. It's possible that the baud rate is different than the bits per second rate when you encode more than one bit at a time. But for what we'll be doing, we'll then just transmit one bit at a time. And if we were to transmit at a rate of 1 bit per second, that would be equivalent to 1 baud. So for our purposes, we'll just think of baud as being the same as bits per second. Right. So a modem, in this example, a modem transmitting binary data at 1200 bits per second is said to operate at 1200 baud. Right. And there are other then systems. Right. Here's an example where there's 16 possible discrete levels you could be transmitting. If you were using a 16-level signal, well, 16 is 2 to the 4th. So basically, you can think of that as 4 times, and you're transmitting at 1200 baud, right? Then the data rate is really 4 times 1200 or 4800 bits per second, because what you're doing is you're able to encode 4 bits on that one transmission. Like I said, so what you should know is that bits per second and baud rate are not always the same thing. For our purposes, we're only going to transmit 1 bit per second, so that will be the same for our purposes. Right? It all depends on your hardware. So data bits, when we transmit information, data bits are what contains our data. And we're going to have to agree then, right, whether we're transmitting 5, 7, or 8 bits, because data is not always 8 bits. You just always agree between the sender and receiver what your format is when you set everything up. In our case, we'll be using ASCII. ASCII then originally went from the number 0 to 127. So there are 128 unique entries in there. So 2 to the 7th is 128, and they use 7 data bits. Right? Extended ASCII uses 8. And when we talk about a frame, typically when we transmit information, we transmit a frame of data, right? Or a single byte. So a single byte, that frame will include start and stop bits, data bits, and parity bits. Right. Typical values for stop bits are 1, 1.5, and 2 bits. So stop bits are used to indicate the end of communication for a single frame of data. That's why it's called a stop bit. When you use more stop bits, there's greater lenience in actually synchronizing the different clocks, but it slows down the transmission data rate. Right. It's all based on the hardware and the way it reads. Right? That's why you can have those different values. Right. Parity is an error checking scheme. Even, odd, mark, space. Right? You can also use no parity. We'll be using no parity in our example, so we won't talk about how to create parity bits or how to deal with them. So here's an example of an asynchronous data transmission. Right? If you want to transmit the ASCII character hex, if we went back then to the ASCII table, we'd see that the hexadecimal representation of that is 53. So 5, hexadecimal 5 is binary 0101, 3 is 0011. And if we set up the serial port settings to have 1 start bit, 1 stop bit, and 8 data bits, that means, and no parity bit, that means there's 10 bits per frame of data that's transmitted, or sorry, 10 bits per frame, and a frame is a byte. And so we always start with the start bit. So in this case, the start bit, then when we start transmission, we go from high to low for 1 bit period, and then let's see what's transmitted. The least significant bit is then transmitted next. So in this hexadecimal 5-3, well, 3 is 0011. So this looks like we've inverted it. There's 0101. That's 5, that's 3. But the least significant bit is transmitted first, then the next, then the next, then the next, all the way. The most significant bit is the last of the data bits that are transmitted, and then finally a stop bit is transmitted. And the stop bit is high. The start bit is low, the stop bit is high. And that's one character or one frame of information. So that's what it would look like if you were to put this on an oscilloscope and see the zeros and ones for transmitting the letter S. Right. There are lots of serial communication architectures. Morse code was one of the first one. There's different specifications, RS-232, 422, 485. We're commonly familiar with USB, Universal Serial Bus, but FireWire, Ethernet, even some fiber channels are serial communication. So it's widely used in our devices. So if you want to talk about a serial port, when you work with an operating system, when we worked with the Blink sketch, we looked up on Windows and we saw that our serial ports were listed as what are called COM ports. On Unix, Linux systems, they're sometimes TTY ports. So you'll see TTY S0 for a serial port, or you'll see TTY USB 0 for a USB port. But the term serial port traditionally identifies hardware that's compliant to this RS-232 standard, but you'll often hear the term serial port as well. All right, we're more concerned about their symbolic names when we need to connect to them via software. Right. So the Arduino itself, it's serial hardware. Right? It has onboard TX and RX connections. So it has it's built into it, it has then a serial port. It all depends on which board you're using as to how many ports. The Uno has 1 port, the Mega has 4 ports. This just talks a little bit more about the zeros and ones. Arduino is using 0 volts to represent a bit value of 0 and 5 volts to represent a bit value of 1. Well, that's on the Arduino Uno and the Mega. Right? The Due or the Leonardo may use something different, but that's all referred to as TTL level. And that relates to the transistors that were used to create this scheme, transistor level logic. And traditionally, right, we don't always get exactly 0 volts. When you're measuring a signal, you might be getting 0.1. You're going to get a range of voltages. Same way you don't always get 5 for high. You might have 4.8 or 4.9. So what transistor logic does is it says any voltage that's above 3.5 volts, right, between about 3.5 and 5, that'll be considered high. Any voltage that's below 1.5 volts will be considered low. Right? So it's not exactly 0 volts for low, it's a range of numbers. So below 1.5, right, for low, above 3.5 for high. Right. And so on the Uno, right, that has the Atmega 328P, as its microchip, it has a built-in what's called USART. It's a universal synchronous asynchronous receiver transmitter that receives and transmits data serially. Right? And if you look at your Arduino board, you'll see some LEDs that are connected to RX and TX. So RX is pin 0, TX is pin 1. But you'll see when when the Arduino is receiving, the LED connected to this pin will blink. When this is, sorry, it won't blink, it will be on. And when this is transmitting, this LED will be on. Right. If you go in and you look up the USART, you're going to see this block diagram. There's a baud rate generator in there, right? There's some synchronization logic. There's some multiplexers in there choosing what's going on with these different lines. There's a transmit shift register. So here's the main area. There's 3 main areas. There's a clock generator. Here, that's your baud rate generator. There's a clock taking care of that, right? There's a transmitter. So there's a set of buffers for the transmitter. There's a set of registers that controls the transmission. There's a parity generator in there as well, right? But here's your output data, your transmitted data. Then the third area, right, receive. So it's got a line for transmitting, a line for receiving, right? So the received data comes in, right? The data is recovered. So when this comes in, remember the data has a start bit, stop bit, it might have some parity bits, so it needs to then pull out the data from there, pull out the parity bit if there is one, check the parity bit, And the data then, right, the data that are received are put into the received shift register, and then we can read that after that's taken care of. Right, after this data is in here, we have the opportunity to read this information with our program. All right. So we're going to use asynchronous mode. All right, and let's actually, I'm just going to skip over to, this just kind of repeating about the start bits and stop bits. Here's an example here, the letter A. Actually, this should say S, that's a typo, let me fix it. It's the same example we saw before with the S. Right. What we're going to do when we use the Arduino is we're going to use some default settings. So we're going to work with 1 start bit, 1 stop bit, 8 data bits, and no parity bit. Our first program will use the baud rate of 9600. So on the Arduino, we'll see then it'll take 10 bits to send 1 byte of data, because we're adding the 1 start bit and the 1 stop bit to the 8 data bits. Right? So if our baud rate is 9600, and we send then 10 bits, it takes 10 bits for a byte, 9600 divided by 10 will allow us to send 960 bytes per second. Right? When you're transmitting and receiving information, a lot of times that rate is important depending on the amount of information, right, and depending on how quickly your program needs to process that. Right. All right, let's take a look then finally at some of the Arduino serial library functions that we'll be using. Right. Well, it has then, we don't have to write any code, right? Arduino is very user-friendly. It has a library called Serial. Right, here's a link then to that reference. We'll use serial read, we'll use Serial.print, println, we'll use Serial.begin. So we'll use all these functions that are already written for us, and we'll learn how to use them. The first thing we need to do, right, is we have to configure the serial port connection with a call of the Serial.begin function. Right? So there's 2 ways you can do it. You can call Serial.begin and you can pass it a speed. The speed you pass it is going to be a baud rate. Right? And that will use that default configuration of 8 data bits, 1 start bit, 1 stop bit, no parity bit. If you need to configure it differently, then you can pass some configuration information that you can find on the reference page. But for our purposes, we're just going to always call Serial.begin and pass it a baud rate using this default information. Right. Your baud rate and your configuration parameters always depend on the hardware device with which you're communicating. So Serial.begin, that function is called in the setup. Remember, setup, that code executes once when the program whenever the program first starts up. So we only ever set up the serial port once. Once we set it up, basically this function enables that hardware. Think of it as turning on that hardware. It sets everything up, and then we're able to use the other functions in the library after that. When we want to write information to the serial port, there's more than one function to do it. Serial.print, we call this function, we pass it some sort of either value or variable name. And what it does is it transmits. So Serial.print transmits, right? It prints data to the serial port as human readable ASCII text. That's what this does, right? It doesn't add a new line character to the end of data. And so I'll show you some examples of that. The function actually returns some information. The data type, return type is a size underscore t, which is simply assigned long. And that tells you the number of bytes that this was able to successfully read. A lot of times we don't query that information, but if it's important for your application, you can query that information. Right? So here's some examples then. Of how to print out some information. Let's look at this example. If we say Serial.print and we type in the integer constant 78, well, we're just going to see the character 7 and the character 8 printed out on the screen. It's going to look like the number 78. But we can then print out integer constants. We can print out floating point. So we can print out integers, floating point numbers. So if you were to print out this floating point number, you're going to see by default it only uses 2 decimal places. We'll learn then how to control the number of decimal places if we want to change that. If you want to print a single character, you can do that. If you want to print a string of characters, you can do that. Right. Then the other thing you can do is notice that in this example, we only then pass one argument. Right? Here we can then pass two arguments to the print function. When we do that, the second argument is considered a format specifier. And whenever we're working with integers, right, we can specify the formats bin, oct, DEC, decimal, hexadecimal. So whenever we specify those, we can get this to write in different bases. By default, the Arduino is always going to transmit or print that information in base 10, right, if we have numbers. But if we want it to print in the other bases, we can then pass this additional argument. Now that works for integers. For floating point numbers, this format parameter specifies the number of decimal places to use. Right. But we'll see an example of how to use that. Here then, if I said Serial.print 78, and then specified this argument, right, it has to be spelled just like this for Arduino to recognize that we should write binary. Well, there's binary, the binary string for 78. OCT octal, there's octal for 78. DEC decimal, that's the default, right? We'd see 78. And then hex gives us 4E. Now here, if we're using then a floating point number, and here I should have been consistent, this says print. Well, println adds a new line character to this, right? But here the second argument, 0, then says print out 0 decimal places. So with integers, this argument then controls the base that they're displayed in, right? With floating point numbers, a second argument here is always numeric, and it always indicates the number of decimal places. Right? There's no guarantee that it will round up. Sometimes it does, sometimes it doesn't. That all depends on the way floating point information is handled. So don't believe that it will always round up, because it won't always do that. Right. So the other function then, right, println, that will append the new line character to it. It works the same as Serial.print, but all it does is appends a new line character to it. It might be an ASCII 13, which is a carriage. So it's followed a carriage return and a new line character are two different things. Carriage return just moves it back to the start of the same line. New line character back to the start of the line and on a new line. So ASCII 10 or back the escape sequence \n is the new line character. But sometimes it's a little bit different on some systems or some devices. Right. In what we're going to see here is we'll see the ASCII 10. Right. All right. We'll work with a program called the Serial Monitor. We'll be able to open this up so that we can see the information on the screen. All right. So let's just go ahead and then write our first Arduino program. Right. Part 1 of our lab then will be to print out this information. All right. So here, let's minimize this, and now let's write some Arduino code. Right. And all right. Okay. Well, font text of 18. All right. Part 1, we're going to transmit integer and floating point data, right? Using the Serial.print and Serial.println functions. All right. All right, so in setup, right, we have to then go ahead and we're going to say Serial.begin, and we're going to use a baud rate of 9600. Right. You can't use just any baud rate. I'll show you some of our choices in just a second. Right. We have to do this then to set up the serial port. Right. So enable serial communication. So, we're going to use the default configuration of 1 start bit, 8 data bits, 1 stop bit. Right. 10 bits. Per byte. All right, that sets everything up. But now in our main code, and notice I have to say serial, we have to use the dot operator, and then we call this function. This is actually, so to remind you, Arduino is C++. So serial is actually a class that's been written, and the way it's been written, you have to then use the serial. It's got a static constructor here, so we have to say Serial.begin and now Serial.print. Right. But let's just do that example of 78 that we saw in the lecture notes. Right. So I've already connected an Arduino, right, to my computer. Remember then, if you want to see here, you want to check your board. In this case, what I connected, I'm working right now with an Arduino Mega, right, this board here. If you're working with an Uno or some other board, choose your board. Here, my COM port, I'm actually on COM 4, this says on my machine. If I want to double check that in Windows, I can just open up the device manager. Right, so I can go to the search function. I can type device manager. It opens this up. I look under ports. Right here, you can see that my Mega is indeed connected to COM 4, which is tools, port, COM 4. Remember, we have to be connected on the right port. And now if I want to upload my code, I'm just going to upload this, right? And it's going to prompt me to save this. Right, I just saved it as serial part 1 on my desktop. Right, it's now checking the syntax, it's uploading. So it's still compiling. All right, and it uploaded then, right, the sketch to my board. All right, so now what I want to do is, what this program is doing is it's transmitting this value of 78. Remember, this main loop runs over and over. In order to see that, I'm going to open up the Serial Monitor program. So I can go to Tools, Serial Monitor, or I can type Control-Shift-M, or I can go to this icon here. That opens up the Serial Monitor. And anytime you start the Serial Monitor, that will start your program from scratch. And I'm trying to figure out why mine did not pop up. All right, popped up on the other screen. So what this is doing is it's just writing out the number, the character 7878 over and over again. Now, I don't have any delay in here. So the serial monitor then is having a little bit of trouble keeping up. I'm going to close that, and let's just put in a delay, and let's say transmit once per second. Right, if I call that delay function, remember that takes milliseconds, so 1,000 milliseconds is 1 second. And if I now re-upload that, and then start the serial monitor, right, so now we can see this is going a little more slowly. It's writing all of this on one line. Right. Notice here in the serial monitor, down here, 9600 baud. The reason I can see this right now is the fact that here I told this to transmit at 9600 baud. This is the transmitting software. The serial monitor is the receiving software. It also has to have the same baud rate, and it always comes up with a default value of 9600 baud. And in this case, no line ending. That's not important. That's more important for part 2, we'll talk about that then, but let's open up 9600 baud. See these different baud rates? So if I select a different baud rate here, it restarts the program, and instead of seeing a 7 and an 8, I see a tilde, and it looks like a 0 or a phi, perhaps. So what's happening is when I do this, over here, this is transmitting 7 and 8, but it's transmitting at 9600 baud. 19.2 is twice 9600. This is sampling at twice the rate this is transmitting. And because these two are working with different clocks, different baud rates, then this is sampling more often, and it's not giving us the same data, right? It looks like we have corrupted data. And indeed we do, because we're transmitting what we want to be a 7 and an 8 here, but that's not what we're receiving. Similarly, right, if I change that to some other baud rate there, we see we get a different set of characters. This is now sampling 4 times faster than this is transmitting. Right? So you can see then, right, at these different baud rates, now I'm not getting anything. It just doesn't even have a printable character. So if you start getting what appear to be garbage values, right, you want to always check to make sure that your transmission software and your receiving software are both operating at the same baud rate, right? And notice then there are fixed baud rate amounts, right? It's due to the clocks and all inherent in the hardware, so you can only use one of these valid amounts. You just can't use any amount, right? All right. Now, what we can do, I'm just going to close this. What we can do here is, there was the print function and there was println. So println means go ahead and print the information, and then when you're done, start on a new line, right? So append the new line character to that is what that's doing. So this is going to transmit a 7 and an 8 and then a new line character. So if we open up the serial monitor again, notice now the 7 and 8 each appear on their own line. All right. And now if we want to see these in different formats, well, we saw by default this was decimal. Let's just go ahead and let's print out a little message, Serial.print. I'm going to say decimal. So we can type in character strings. That's just going to print out the characters in here verbatim on the screen. All right. If we re-upload this, now sometimes this will work with your serial monitor program open, but now you can see we get decimal and 7/8. So that's telling us our base here. All right. Now notice here I just typed print. So this would print out decimal, colon, space, and I didn't want it to go to a new line because I wanted the 78 to show up on the same line. And then I want to start a new line after this, so the println appends that new line character to that. All right. And so if I say Serial.print binary, right, Serial.print 78, and then bin, we upload this, now we're going to get, oh, I forgot my println here, so I got just what I asked for. My print new line. All right, so there's my 78 and there's my binary. Right. Similarly, say Serial.print hexadecimal. Serial.println. Here's my 78, and here I am in hex. Right, and sometimes when this first starts, you'll get some corrupted information on the first line, or it might look like it skips the first line. All right. So now we're getting that information. So you can see then that works with these decimal constants. It works with variables as well. All right, let's then create some global variables. All right, int, I'll just call this ival, and let's set ival equal to 0. Right. And here, now let's replace the 78 with ival. Let's transmit, right? And then let's just go ahead and add 1 to ival each time through the loop. Right, so now we can see that this works with a variable. We're also incrementing the variable through the loop, so we can see that these are changing. So we can see that then the binary, the hexadecimal, and all is changing as well through that. So there's some examples of integer values. And notice I made this an int. I could have just as well, I could have made this an unsigned int. I could have made it a long. Could have made it an unsigned char or a char. So you can make these different data types. They're all part of the integer family. Right. Now let's just go ahead and create a floating point number. So I'll call that fl. All right, and we'll set this equal to, we'll initialize it to 1.2345678. And now let's go ahead and print out fl. So print and we'll say, let's just say fl here. So we can see the default behavior. It's going to comment out these integers, and let's just concentrate then on the floating point. All right, so we can see we get that default behavior of 2 decimal places. Now, if we wanted to say something like Serial.print 0 decimal places, right? And now let's change this to 0. So that second argument was floating point numbers, and it could be a float or a double, right? Then we see we just get the integer portion of it. Right, you can do a little copy pasting here. All right, now if I want to see 1 decimal place, I can do that. All right, if I maybe want to see 4 decimal places, can do that. Re-upload. All right. So you can see then with floating point numbers, that's going to control then the number of decimal places. And we could turn both of these back on if we want to see both pieces of information popping up there. Right. And if we want to do something like, say, let's say val equals val plus 0.005. We will just go ahead and increase that while that runs through here every time. All right, we can see that changing. Now you can print blank lines as well too. But what if I were to now just say something like Serial.line integers. I could do a \n here if I want, so I can use those control characters. And if I just wanted to get a blank line here, I could say Serial.line Print ln. I think and leave that empty. Let's see if it likes the empty. All right, so notice then, and if I could turn off auto scroll, so when this first printed out, we got integers, and now I got an extra blank line here. Right, we saw this, and then we started getting the floating point information. Now it doesn't seem like we got, actually, we got our blank line here. So if I give this an empty string, and, oh, here, I messed up. All right, so you can play around with this and see you can use some of those control characters. You can get a blank line by doing that. All right, if I turn auto scroll back on, this will keep repeating. All right, and you can do things like other control characters like the \T for a tab. Right, notice how that tab that over there. All right, so that's what you're doing then in your part one. All this is doing is a reminder then is this is transmitting information. So we always have to set up the serial port in order to turn it on. All right, if I don't do that, so if I upload this, right, all I did was comment out Serial.begin, and if I turn the serial monitor back on, notice we're not getting any output, right, because we haven't turned on that hardware. Notice we didn't get any sort of compilation errors, right? We're calling these functions, but we haven't turned on this hardware. Once I turn this back on, both of these are then operating, will be operating at the same baud rate. Now we get our information again. Remember, if I change the baud rate, this is transmitting at 9600, this is receiving at twice that. We don't get the information we expect. But remember, both programs have to have baud rate settings at the same speed. Right? You then saw the difference between print and println, how to use these integers with the format argument, then if you want the different bases, how to use the second argument to control decimal places with floating point. Right? And that was part one, right? You'll be doing, likely, you should be writing the same code if you haven't already. You have a lab assignment for my class, you'll actually be writing this code as well too. All right, that's the end then of this particular video. In the next video, we'll see how to read information.